In this video, we're going to be talking about voltages. So we're going to be figuring out or showing you a different way to figure out the voltages of cells, as well as how to use voltage to identify an unknown half cell. We'll talk about oxidation potential, as well as the importance of order of voltages in your redox half reaction table, so in this table. And then we'll talk about changing the reference. So voltage, what is that? All it is the difference in energy between 2 points on a circuit per unit of charge. So voltage is sometimes called potential difference. So voltages, they can vary depending on how strong of a reducing or oxidizing agent you have. If you have a very strong reducing agent teamed up with a very strong oxidizing agent, you're going to get a pretty big voltage. A reducing agent with less power teamed up with the same oxidizing agent, you're going to have less voltage produced. So voltage has the units of volts, but sometimes it's in joules per coulomb. So joules is just a unit of energy and coulomb is just a unit of charge. And the purpose of building a voltaic cell is to create a potential energy difference, so to create a voltage. Okay, so you'll notice that your redox table shows half reactions with voltages, and we've talked about that previously. Okay, so all of these voltages, they're off on the right hand side, and each half reaction has its own unique voltage. Okay, so they're kind of like fingerprints. So only this half reaction will have a voltage of positive 2.87. So when I say this reaction, I'm reading it from left to right. Okay, so the reduction half reaction, that's the only reaction or half reaction that has a potential energy or electrical potential of positive 2.87. Okay, so these voltages, they're kind of like fingerprints. You can use them to identify what half cells that you have in your cell. So all of these values in our table, they were obtained by building voltaic cells with a particular half reaction and the hydrogen half reaction. The potential differences represent the change in potential between the particular half reaction and hydrogen. Okay, so why is this hydrogen half cell so important? It's because it was assigned to be the reference cell. Okay, so the hydrogen half cell was arbitrarily assigned the value of 0. So we call that, like, if it's assigned the value of 0, then the hydrogen half cell is the reference cell because it has that assigned value of 0. So hydrogen half cell is the reference cell. Okay, now all other voltages on that table are going to be relative to the hydrogen half cell. So any half reaction higher than hydrogen is going to have a positive potential difference, and any half reaction lower than hydrogen will have a negative potential difference. Now, we can determine the potential difference between any two half reactions using, you can either use formulas, one of these two, so you could either use this one, where your potential difference is the potential coming from the reaction that happens at the cathode minus the potential of the reaction that happens at the anode. So in other words, cathode minus anode. Or you could use this formula. These two are, they do the same thing, they just say it in slightly different words. Okay, so you could either find out the potential difference by going cathode minus anode, or you could take the voltage of the SOA and subtract it with the voltage of the SRA. Okay, so you do have a couple options. Okay, this is option 1, this is option 2, but earlier in the notes we have done a different method. So I'll call this method number 3. So we find the potential difference through flipping the sign of the oxidation reaction and then adding up the voltages. So, what we have been doing so flip sign, and by flip sign I mean as a reduction reaction, if it's a positive sign but you're trying to write it as an oxidation reaction, you flip that positive into a negative. Or if it starts out as a negative, flip just means you flip it from a negative to a positive. Flip sign on oxidation, half reaction. And add to the voltage of the reduction reaction. Okay, so you have your choice. Okay, options number 1 and 2, they're the more mathy way to do it, and all you have to do is plug in the numbers and away you go. Whereas the third method, so what we have been doing is you just need to remember to flip the sign on the oxidation half reaction. Okay, you don't need to do that for these first 2 options because the negative sign in each of these does it for you. Okay, so example, find the voltage of the following cell. So we have our first half cell, which is right here, and then our other half cell, which is right there. Okay, so if I figure out where all of these species are, so we have all of these as well as we have water. Okay, how I know I have water is because these are aqueous solutions, so that means that it's dissolved in water, so that's why I know I have water. So if I go and find all of these, so copper, that should say copper solid, copper 2+, zinc 2+, and zinc solid, I'll do that first and then I'll figure the rest out. Okay, the reason why I'm doing that is because I need to figure out what is my reduction half reaction, what is my oxidation half reaction. Okay, so I'm going to start out by just going through the left-hand side and seeing what I have. So we have copper 2+. And since this is the first species that I run into on the left-hand side, that's telling me, okay, copper 2+, that's my SOA. Okay, so the SOA reaction is going to happen at your cathode because remember, red cat gets fat. So reduction happens at the cathode. Your strongest oxidizing agent helps other things to get oxidized, but it itself undergoes reduction. So copper 2+ is being reduced at the cathode. Okay, so let's just go back to our question. So that tells us this is our cathode, which means this has to be my anode. So just as a reminder, your electrodes, both the cathode and anode, they have to be solid. They can't be aqueous, they can't be liquid, they can only be solid. So that's how I know zinc solid is my anode and nothing else. Okay, so now what I can do here is I can choose which method I want to use. Okay, because I've already showed you guys how to do this, I'm going to move on to just showing you how one of these first two options would work. Alright, so just arbitrarily, I'm going to do option number 1. So we're asking ourselves, what reaction is occurring at the cathode? Okay, so potential difference, I just like writing it as cathode minus anode, because I know for both I'm going to be using the electrical potential. So I'm going to find the reaction that happens at the cathode, which is copper 2+ being reduced. Okay, and then I'm finding, okay, that has an electrical potential of positive 0.34. Minus, now for my anode, okay, remember we're talking about what is the reaction happening at the anode. So that reaction is going to be tied to the SRA. Okay, so I'm going to just find out, okay, what's my SRA? And just make sure that it's the same. So keeping all of my chemical species in mind, copper solid, copper 2+, water, zinc 2+, and zinc solid. Zinc solid is the first one I run into, so that's my SRA. So the reaction happening at the anode is this as an oxidation reaction, so we're reading it backwards. So zinc solid loses 2 electrons, and in the process zinc 2+ ions are produced, and the electrical potential is negative 0.76. So I'm going to write that negative 0.76. So if I go a negative times a negative, well, that's a positive. So that's the mathy way to flip, quote unquote, flip the signs, okay, is with this negative here. Okay, and then we just add 0.34 with 0.76, and that's going to give us 1.10 volts. As a reminder, for this answer, I've already put it in the correct amount of sigdigs. Remember, when you're adding or subtracting numbers, you're always going to the number that has the least amount of sigdigs after the decimal. So since both of our values have 2 significant digits after the decimal, then that just means that I have to have my final answer with 2 sigdigs after the decimal. Okay. Alright, so method number 1 and 2, very similar. Okay, if I was to show you the way that we have been doing it, what I would show you is I would say, okay, the reduction half reaction, we're reading that from left to right. So we keep the sign, or we keep the value as is. Okay, so if I was to do that using the method we have been doing, it would look like this. So 0.34, and then with the oxidation half reaction, since we're reading it backwards, we have to flip the sign. So we got to flip it from a negative 0.76 to a positive 0.76. And then you just add them up, and away you go. Okay, so you can choose which method works best for you. Okay, the only difference is this is a little bit more mathy, but you don't have to remember to flip the sign on the oxidation reaction. Okay, or alternatively, if you want to remember to flip the sign on the oxidation half reaction, then you can do it this way. So super important that you're flipping the sign on the oxidation half reaction if you are going with method or option number 3 here. Okay, so just to write this out, this belonged to the cathode reaction. This belonged to the anode reaction, or the reaction happening at the anode. Okay. So the next part of the notes is all about identifying an unknown half cell using the electrical potential. So you can work backwards to find the voltage of a half cell if you are given the net voltage. Okay, so the reason why this works is because all of these electrical potentials on the far right hand side, they're kind of like fingerprints. Okay, so like I was saying earlier, this positive 2.87 only belongs to the reduction half reaction right here, so we're reading it from left to right. Okay, if we were reading it backwards, so from right to left, then it would be negative 2.87. Okay, and that would only belong to the oxidation version of this first half reaction in this table. All right, so we're asked to find the voltage for an unknown half cell. So we're given our strongest oxidizing agent, which is cadmium, and then we don't know our strongest reducing agent, and so we have our net reaction with the net potential, electrical potential, and we also have the SOA electrical potential. Okay, so what I'm going to do to figure this out, this one, it's nicer to use the formula version. So again, I like using cathode minus anode. If you really don't like that, you could also do SOA minus SRA, up to you. Okay, but I like this one. Okay, so SOA, we're told, is negative 0.40 volts. The net potential or electrical potential is positive 2.51 volts, and we have no idea what the anode or the reaction at the anode's electrical potential is. So I'm just gonna have an A for my stand-in for my variable. Okay, and now I'm just gonna isolate for A. So I'm gonna add 0.4 over. So 2.51 plus 0.4, that's gonna give me 2.91 volts is equal to negative A. So I'm using A just for the stand-in for anode, and I'm going to divide each side by negative 1. So that's going to give me negative 2.91 volts is equal to the anode half reaction, or the reaction happening at the anode. Okay, so now that we have this is what we can use to identify what our SRA is, or what the half reaction is that's happening at the anode. So if I go to my table and I find negative 2.91, I'm finding it right here. So let's clean this up a little bit. So that means that the half reaction happening or occurring at the anode is this one. Now keep in mind, at the anode, an ox gets thin. At the anode, oxidation happens. So we're reading this reaction backwards here. Okay, so based on the voltage, what is the identity of the unknown half cell? It's going to be this. Barium solid produces 2 electrons and barium 2+ aqueous. Okay, moving on to oxidation potential. So on page 7 of your data booklet, reading all of the reactions from left to right, it gives you all of the reduction half reactions in that table. Okay, so the electric or electrical potential values, they are all for reduction electrical potentials. Okay, so the oxidation potential is simply just the opposite value because it's the opposite reaction. Okay, and we've talked about this before. So for example, the reduction potential for silver ions is positive 0.8. Okay, but if we are trying to reference the oxidation potential for those silver ions, because it's the opposite reaction or the reverse reaction of a reduction reaction, then you're just flipping the sign. Now, with the redox table, all of the electrical potentials, they're listed from most positive at the top to the most negative down at the very bottom here. Okay? So the most positive potential, electrical potential, belongs to your strongest oxidizing agent. The most negative reduction electrical potential, that belongs to the weakest oxidizing agent. Okay? And again, if we flipped these values, then it would belong to the reducing agent. Okay, so with the reducing agent, if we're writing this last one as an oxidation, then we just flip this sign into positive 3.04. Okay, so the redox table in your booklet is listed from most positive to most negative. So that's important because order, as the title says, order is important for these reactions. If you're given a list of half reactions with voltages, make sure that you list them from most positive to most negative before you find the SOA, SRA, so on and so forth. Okay? So, with that, we're given an example. Calculate the electric potential difference when the following pairs of half reactions are combined together. Assume that the net equations are spontaneous. So remember, the more negative the electrical potential, the lower on the reduction half reaction table you will find it. Okay, so we're given our first reaction, our A1+ ions gain an electron to give us a solid, and that electric potential is 0.2 volts. Then for the next one, our B ions, B1+ ions, gain an electron to give us B solid, and the electrical potential difference for that reduction reaction is 0.5. Okay, so figuring out what is our SOA, what is our SRA. Okay, the more positive your electric potential, the higher up you're going to find that reduction half reaction. Okay, so that means that the reduction half reaction with the more positive electrical potential, that's going to belong to your SOA. Okay, so I'm going to call this my SOA, then that means that this has to be my SRA. So we're asked to figure out, okay, electric potential difference, so E, and then I'm also, like again, I prefer cathode minus anode, but if you want to make life easier for yourself in this question, you can go SOA minus SRA. Okay, so you'll have 0.5 volts minus 0.2 volts, which will give you 0.30 volts. Okay, and I've already done significant digits on that. Okay, so keep in mind with questions like this where we're talking about electrical potential, sometimes they do like to give you situations where you don't know the identity of the either ion or metal. Okay, so that's why we're talking about how order is important, so that if you don't have the identity of whatever substance you're talking about, you can still figure out the question because you can use the electric potentials to figure it out. Okay, because the electric potentials will tell you what is a better SOA versus like a SRA. All right. Moving on to changing the reference. So we said that hydrogen or hydrogen half cell, that is the reference for this entire data table here. Okay, so if I find the hydrogen half cell, it's right here, and it's got an electric potential of 0 because it's the reference cell. Okay, everything else in this table is based off of this reaction. So the hydrogen half cell is the typical reference cell. Which means it's assigned a value of 0. Okay, what these types of questions are asking is, what if hydrogen, that hydrogen half cell, was no longer the reference cell? What if it was a different half cell? That's what these questions are asking. So we're asked, find the voltage of a zinc half cell if copper is assigned a value of 0. So what does that tell us? That tells us that copper is our reference cell here. So it's our new point of reference instead of hydrogen. Okay, which I should be writing that as H2. All right, so we do have this little note over here that says that the net voltage for a cell never changes even if the reference point does. So that's really important here. Okay, so using that to inform me, okay, what should this voltage of this zinc copper cell be, even if we have copper as our new reference cell? what that means is it's going to be the same as it was before. So we've already done this question here. So we've done it up here. And before, so this is when hydrogen was our reference cell. Before the electric potential or the electrical potential difference, we found that was positive 1.10 volts. Okay, so in theory, despite us having a different reference cell, this should have the same electrical potential difference. Okay, so let's just prove that and write out some stuff. So copper solid, that was our cathode. Our SOA was those copper 2+ ions. Zinc solid, that was our anode. It was also our SRA. Okay, so I'm going to be looking at the electrical potentials for the SOA reaction and the SRA reaction. Okay, so copper 2+ right here. So with hydrogen as its reference cell, it has a reduction electrical potential of positive 0.34. Okay, but this question is saying that this half reaction here, because it contains copper, that is our new reference cell. Okay, so we're going from positive 0.34 to now it has a new assigned value of 0. So let's just write out what's happening here. So we're going from positive 0.34 volts to 0 volts. So we got to ask ourselves, okay, mathematically, how do we get from positive 0.34 to 0? Well, you subtract 0.34 volts. Now for our SRA reaction, so that was with zinc solid. Let's find that here. So zinc, that's right there. So with hydrogen as the reference cell, its original reduction potential value was negative 0.76. Okay, but now since we have a new reference cell being the copper reaction, we got to apply the same changes that we applied to the copper cell. So minus 0.34 volts, so negative 0.76 volts minus 0.34 volts, that's going to give us negative 1.10 volts. Okay, so if you wanted to find the change or the difference in electrical potential, so you could write this as SOA minus SRA or cathode minus anode, whatever you prefer. I'm just going to do, for now, SOA minus SRA. So our SOA, that was the copper 2+, that had a new electrical potential of 0 minus negative 1.10 volts. So a negative times a negative is a positive. So this is going to give us positive 1.10 volts. Okay, so there's your proof that when you change your reference cell, it's not going to change the net voltage or the electrical potential difference between your SOA and SRA. Okay, so now that we know how to make changes to our reduction electrical potentials when we have a new reference cell, now we can move on to this question. So what is the standard half cell potential for the reduction of silver ions if this reaction is our new reference cell, okay, or is assigned a reduction potential of 0. So that just tells you if we're assigning this a reduction potential value of 0, that's the new reference cell. So let's find this reaction in our data booklet. Okay, so it's right here. So originally, with hydrogen as a reference cell, it has a reduction potential value of positive 1.36. So let's write that out. So if it gets assigned a value of 0 volts, we ask ourselves, okay, how do we get there? Well, you had to subtract 1.36 volts. Now with the silver ions, okay, let's figure out where that is. So silver ions, that's right here. So with hydrogen as a reference cell, its reduction electrical potential is positive 0.8. So since the reference cell changed, we have to apply the same change that we applied initially. So minus 1.36, so 8 or 0.8 minus 1.36, that is going to give us negative 0.56 volts. Okay, so this is the new reduction electrical potential for silver ions. Okay, using this as the new reference cell.